Erica with Rosie Research, and last month we had a great time defeating our Asteroid of Doom. We learned about how plastic optics of different shapes can bend light in different ways, and then we even got a chance to make a tasty treat with Jell-O and use that to make our own lenses. But now that our Asteroid of Doom is completely obliterated over the night sky, we have to track all of those pieces. And it's just way too much for scientists to be able to do on their own. And they need us as sky watchers to be able to help them make sure that there's no things that are going to come into Earth and hurt us. So what we're going to do this month is make our own telescopes and turn them to the night sky and do some sky watching. So the first part of our lab is obviously our story, and that's always the funnest part to read to your kids and get them engaged in the science. And then we have some stuff about looking at the lenses that you get. Now you can get all sorts of different lenses. I found that Google VR lenses are really easy to source. They're pretty cheap. If you're doing a classroom pack type of a thing, if you want to do with a classroom, you can get a package of 100 lenses for about $20. So that's a really good option. If you're just doing it with yourself, options are using magnifying glass lenses that you can find easily at like the dollar store. You can use reading glass lenses for your long focal length. So you'll have two. You'll have one that's a really long focal length and one that's a short focal length. I also have some sourcing links on where you can buy these pretty easily online. But what I have are two Google VR lenses. This one is an 80 millimeter focal length and it's about 30 millimeters in diameter. And this one is a 10 millimeter focal length, which is my short one, and it's, I think, 17 millimeters in diameter. And what we're going to do first is we're just going to look at our lenses, and this gives the kids a chance to sort of touch the lenses and play with the lenses. And the great thing about this is that they're plastic, so you don't have to worry about fingerprints or smudges or scratches or anything like that. This is all meant to be fun. Before I did this, I couldn't find my ruler, so I just went online and got a ruler. That is pretty easy. The one thing to note is when you buy your lenses, it should have focal lengths which are typically given to you in millimeters. So you can either convert that to inches if you're in the US and you want to work all in inches, or just measure everything in millimeters. So the first thing that they get to do is just sort of measure a few things. So over here we have the measured values of the diameter of our lens. So I can just set my lens on top of here and look at the diameter, so across the fattest part of my circle, and I would say that is about 30 millimeters. So I can write that in. And then it says to measure the thickness, just to sort of have fun with that. And that's a little tougher because this one's very thin. Your short focal lengths could be really bubbly, it might be a little bit more fun to measure. But I would say that this is maybe, I don't know, 4 or 5 millimeters, so I'll put down 5 millimeters. And it doesn't have to be perfect, that's the whole point of this. And then they get to measure the focal length. One way to measure the focal length if it's sunny outside is to just put it right above your paper and look for where you get the sun really focused on your paper. If it's not super sunny outside or you're doing this indoors, you can use a flashlight. And so what you'll want to do is you'll have your flashlight on and you're going to go up and down until it gets into focus, and then you'll measure that area where it's at. Let's see. And you want to go through your focal point always so that you know that you got in focus. So it should be really fuzzy, and it'll get nice and clear, and it'll be really fuzzy again. So I'm going to go for about right here as my focal length. And then we can just stand this up and measure it. Let's see. So I feel like I'm moving it here, so let's try this again. Alrighty. So maybe about right there is where I get my guys. So I'm getting about 135 millimeters. Okay, and then the next part is to look at the actual values. Those you're going to just read off of your package. So this one does have a 30 millimeter diameter, and its focal length is actually 80 millimeters. So I was pretty far off. And that's okay. That happens in science. Maybe I'm not getting a very good reading because this is somewhat close to the lens where the sun is really far. So if it was from the sun, maybe it'd be a better reading. But so then they have a chance to look at how accurate they are. And this is something that as scientists we do all of the time. We look at what our error is. And so it's got sort of these cute little boxes. You fill in the numbers. And as long as you're in the same unit, so as long as you're all in inches or all in millimeters, it'll work out well. And you'll get like a little percentage. And you can see how close were you. And so you'll do that with both of your lenses if they want to. And again, all of this science stuff, you want them to have fun. So if they're engaged and they're interested and they're having fun measuring, they're having fun playing with the lenses, definitely do this piece. If they're kind of like, meh, I want to go on to the building part, go on to the building part. So the next part is they're going to make their telescopes. And what you need are some either toilet paper or paper towel tubes. I found the paper towel tubes at our high school actually had really nice thick paper towel tubes that didn't kind of scrunch very easily, which was really nice. And you want them to be able to fit pretty snugly inside of each other. Now, if you can't find two that fit really nicely like this, what you can do is you can find one that's really big and then cut it, and you'll scrunch it right around this guy, and you'll add a piece of tape right there so it'll kind of keep it where it's nice and snug. So you have your two pieces of cardboard tubes. You need two lenses, so one needs to be a long focal length lens and one needs to be a short focal length lens. And that's what brings, the long focal length lens brings all of this light into your eyes and it makes this big image come sort of down. But the short focal length brings it back so it looks like it's like a perfect image instead of the rays of light coming straight in and being fuzzy maybe. It makes it so it's nice and clear. So the combination of the two of these is what gives you a nice, clear, sharp, enlarged image. So you'll need that, and then you're going to need just a piece of like either thin cardstock or paper or cardboard. And what you're going to do is you'll take your two toilet paper tubes or cardboard tubes and you're going to put it on your cardstock paper and you'll just draw a circle around it and you'll cut that out. So you'll get a cutout circle of this piece and then you'll trace around your lens in the middle of it so that you kind of have this nice hole, and that will let you glue your lens in like this, and then you can glue it onto the top really nicely and easily. So you do that for your larger lens, and then you'll also do the same thing for your smaller lens. You can just kind of pop through it. And so what you have after you glue those ends onto this is a fabulous telescope that looks like this. And one of the fun things that we do with our kids' astronomy program is they always get to decorate things, and that kind of makes it uniquely theirs. So give your kids a chance to decorate it. Maybe you have some gems that they can hot glue on, maybe just markers and paints. We had little eyeballs that were going on these. We had nice little things to look through as spotter telescopes, anything that they want to make it theirs and make it fun. And the last thing you're going to need to do is that this telescope goes in and out. And you're going to need to look through your telescope and go in and out until your picture is nice and clear. So for me, that's about right here. If I go further in, it gets all blurry and fuzzy. And if I go further out, it's blurry and fuzzy. And one way, if you're having trouble getting it into focus like this, is you can add your two focal lengths. So here I have an 80 millimeter focal length and a 10 millimeter focal length. So I can say 80 plus 10 millimeters. 90 millimeters is about how far these lenses should be apart. And that can give you kind of a ballpark starting part. And if you want to, you can tape that right there so that you always have this and it can never get smushed or not. Or if you enjoy sort of trying to find it, you can find the focal length every time. Not a hard process. One thing you'll notice, however, is when you look through this, everything is going to be upside down and turned around completely. And we saw that actually when we did our ray tracings with the plastic optics in last month's lab. And what we're going to do is also look at it here and see. So one of the activities that they can do is a little bit of a ray tracing of a rainbow tree. And if we take a look, it has an example of a red triangle at the top of the tree, and the light from that red triangle goes straight out and into our lens, which is going to focus it to a focal point, which for mine was 80 millimeters away. And it's going to keep going through that focal point, but then the 10 millimeter lens, because it's in the perfect spot, is going to send it out nice and parallel for my eye to see clearly. But you'll notice now that it went from the top to the bottom, which is why it's upside down. And so we can trace this for the other pieces of our tree, and we can add in our tree triangles. And this gives us an idea of what is going on with why our image is flipping over. And you can imagine if it's flipping top to bottom, if I look at it from a different side, it also flip from side to side. Like this, and then we'll put the brown in pencil. So there's my tree, and it's flipped upside down. It's also going to flip from right to left. So everything is going to be flipped around. So you didn't put your lenses in backwards if you're upside down and everything is flipped side to side. You put them in perfectly right. It's just that that's how optics work. So it goes from the top, and as it bends the light, it bends it down. So it's coming down, and then it goes out. So now the top is at the bottom, and the bottom's at the top. And the same thing happens from left to right. The right is at the left, and the left is at the right. So they can do that to check it out. They can also ray trace their own telescope. So what you would do there is you would measure the focal length from your long lens. So for me that was 80 millimeters. So I would put a dot there as my focal length. And then 10 millimeters after that is where my next lens comes in at. My nice little bubbly lens. Like that. And so what I can do then is I can ray trace my own picture. So I'll go from top of the lens through my focal point down to the bottom, and then it'll come out nice and straight. And I can do that in the bottom of my lens also, and you'll notice the bottom of the picture goes up to the top. And it's going to come out nice and straight. And I can do that as many times as I want. The one in the middle will come through. And so if I had any picture that I wanted to draw, let's say this time it'll be a person, that person will come out here and they will be flipped over and smaller. And to my eye, when my eye is right here, it's going to take up much more of my eye, which is what's going to make it seem so big. Is that it takes up so much more area on the back of my eye because that image is really close to my eye now. So if they want to do that, that's great. And once they've done that, we also have a way for them to measure the magnification. So what they can do is they can sort of look through their telescope. You tape this up on a wall. They'll look through the telescope at the small square and think about how much of their eye does that take up? How big does it feel to them? And then look at the wall at the other squares and say, oh, it seems like maybe that looks like it was 3 times magnification, like it was 3 times bigger or 8 times bigger. And you can also, once they do that, you can also look at how accurate you were. So to figure out your actual magnification, you divide your 2 focal lengths. So here I have 80 millimeters for one of them and 10 millimeters for the other. So I get an 8 times magnification with this telescope. And then you can look at how close was I? Did I say it was 3 times magnification when the math says it should be 8 times magnification? And why would that be? And likely because there's a lot of human error, right? There's a lot of observation in that and a lot of what do we think happens and what do we think it looks like versus the math, which is just what it is. And then the last part of this lab has sky charts for you to look at in the northern hemisphere based on what season it is. And this is a really fun thing because it kind of sets up a good parent-kid date for you guys where you can look out into the night sky and see how many constellations can you find. We also have the major meteor showers and how you can find them with your telescope. So you can take, if you want to do a meteor shower tracker and start counting how many meteors do you see per hour or per 10 minutes maybe. And you can draw the sky that you see if you'd like to. And we have a lot of sort of add-on activities. One of the things that younger kids might have a lot of fun doing is looking into the night sky and sort of tracing over all of these constellations as they see them and seeing kind of as an I spy, how many of these constellations can I find? When can I find Orion? And once you find Orion together, you guys can sort of trace in Orion so you know, hey, I found that. And if you want to, you can get some books from your library. You can read some of the mythology about Orion, and you can look at how we got these names for these if you want to. And that's kind of a fun way to track through the night sky and see what you can find and sort of make it into a game, an I Spy game. I know my kids absolutely love sort of games, and my older one is goal-oriented. She would want to find every single one of these, and that's what would drive her, is just coloring them in. And some of our other add-on activities are making constellation cookies, which are delicious and fun for all ages. And then for grades 2 and 3, we have a planetary finder. So how do we find planets? And there's actually a bouncy ball sky, and there's some planets that are changing in different ways in that sky. And it kind of asks you, can you find it? So it's a big I Spy. It's really hard. Even when I know the answers, it's hard for me to find it. And it can bring up this conversation with your kids about how do astronomers do these things that are really hard? Do we do it just by brute force and always just spending all that time? Or do we try to find different ways that are better to find things? And for example, astronomers do something called a blink comparator, where they look at one picture and then another, and then they kind of blink these two pictures. And when you're blinking the pictures, you find that planet that's changing so incredibly quickly. It's astonishing. And I've made blink comparators for all the different types of planets that are in that, and that's in your add-on package. 4th and 5th graders have the chance to also find Pluto from the real data that they used to find Pluto way back when. And that gives them a chance to think about, how do we see planets across the sky? How do they move? And when they're moving, what do we see them doing? So that's another add-on activity. You can make 3D constellations, which is kind of fun for maybe a little bit older kids. But one thing that we think of when we look at the night sky is all of our constellations are two-dimensional. And so our Big Dipper just looks like that handle, and all those stars are in the same plane. And that's because they're all so far away from us that they look very much like it. But in reality, these stars are at all different distances from us. And so by making a 3D constellation, you can kind of bring that home and see that how vast space is and how far some of these distances are away from us, even though they look like they're in the same plane and like it's two-dimensional, but it's not. So that's what we have in store for you guys this month. And next month we've got some really fun stuff we're working on with particle physics. And we're going to save some time travelers with paint and marbles, and a lot of fun with that one too. Thanks for joining us, and we'll see you next month.